Hello everyone, welcome back to my channel. In this video, I'll tell you how to design 1011 sequence detector using Mealy FSM, and in next video, I'll describe same 1011 using Moore FSM. So basically, sequence detector is a circuit which detects incoming bits. If the incoming bits will come as per our expectations, like here expectations are 1011, then it will generate output 1, else output will remain 0. It is very important to understand steps we must follow to design 1011 sequence detector or any sequence detector. So very first is you must draw state diagram. If your state diagram is correct, then from that state diagram only you will write state table, and then by using excitation table you will generate equations for input and output. Then next step is K maps. By putting those values in K maps, then you will get equations, simplified equations, and then based on those simplified equations you can draw logic diagram. So here let's start with state diagram for 1011. In Mealy FSM, generally number of states in state diagram are same as length of our sequence. So here length of our sequence is 4. So number of states will be 4. So I'll start with first state. I'll mark it as S0. Instead of S0, S1, S2, S3, you can also use ABCD. That is okay. And in case of Mealy FSM, in Mealy FSM, output depends on present state as well as present input. So here, if my first bit is 1, my first bit must be 1, and if correct bit will come, then it will go to next state, and my next state is state 1, S1. If 1 will come, and output will be 0 when entire sequence will get detected. Only one bit is detected, so output will remain 0. But if instead of 1, if 0 will come, it is possible that 0 can come, then it will remain in same state, and output is also 0. So if correct bit will come, you need to remember state diagram is very important. If correct bit will come, then only it will go to next state. At S1, what is my next correct bit? 0. So if 0 will come, it will go to next state, and my next state is S2. If 0 will come, it will go to next state. Output is still 0 because entire sequence is not yet detected. But what if 1 will come? It is possible that first bit 1 will come and then next again 1 will come. Then it will remain in same state and output is 0. 1, 0. So left hand side of this slash is input and right hand side indicates output. It is not like if wrong bit will come, then it will remain in same state. No. You'll get it after some time. So see here, if 0 will come, it will go to next state. Next, if 1 will come, next correct bit is 1. So if 1 will come, it will go to next state, that is S3. If 1 will come, and output is 0. What if 0 will come? That is first 1 came, then 0 came, and then instead of 1, it is possible that again 0 will come. Then in that case, if 0 will come, then it will go back to state S0. If 0 will come, it will go back to state S0. And why? Because after 1, 0, 0 is not expected. So we need to start from beginning. So it will go to our initial state, that is S0. Then after this 1, suppose sequence is 1, 0, 1. So first 3 bits are correct. And next, if 1 will come, 1 is my correct bit. If 1 will come, it will go to state S1. If 1 will come, it will go to state S1, and now output is 1 because entire sequence is now detected. Why it will go back to S1? Because first transition to S1 was when input was 1. So to S1 transition is only when input is 1. So it will go to S1. But what if 0 will come? If 0 will come at S3, then it will come to state S2. And it is wrong, that is 1, 0, 1, and next if 0 will come, then it will go to S2. Now why S2? See, In case of overlapping sequence detector, it is possible that this 0 is my second 0. So it is like 1, my first one, then 0, second bit, then 1, third bit, and then fourth one. So see here, it is like 1, 0, 1, 1, 1, 0, 1, 1, or 1, 0, again 1, and then 1. So this is our state diagram for 1011 sequence detector using Mealy FSM. In Mealy FSM, output depends on present state as well as present input. Now let's write state table from this state diagram. So here how many states I have? I have 4 states, S0, S1, S2, S3. So I'll write S0, S1, S2, S3. And now I'll map them into binary equivalent. So I'll write them as 0, 0, 0, 1, 1, 0 and 1, 1. So instead of writing S0, hereafter I'll use 0, 0. For S1 I'll use 0, 1. In this way. If there is fourth state, S4, fifth state, then instead of using 2 bits, I'll have to use 3 bits. Then it will become 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. And for S4, it will become 1, 0, 0. Now, let's write truth state table. So, see here, in finite state machine, we have present states. Like here present state is S0. If input 1 will come, then next state is S1. What we have is next state, input and output. So here present state is, I'll use it as QB and this is QA. So present state is QB, QA, and for input I'll use X. Here next state is QB plus 1, QA plus 1, and for output I'll use Y. So based on value of input and present state, I'll detect next state and output. So here I have total 3 variables, QB, QA and X. So here I'll write truth table as 4 times zeros, then 4 times 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, because I have 3 variables. Now see. Present state is 0, 0. 0, 0 means S0. So when present state is S0, or for understanding, I'll write here S0. 0, 0 is S0. S1, S1, S2, S2, S3, and here also S3. So when my present state is S0 and my input is 0, then next state is again S0. That is 0, 0. Present state S0, input 1, then next state is S1. S1 is 0, 1. Present state is 0, 1, that is S1. If input is 0, then next state is 1, 0. Present state 0, 1 and input is 1. Present state 0, 1 and input is 1. Then next state is, it will remain in same state S1. So 0, 1. See, my present state is S2. I am in S2, 1, 0. And if input is 0, see here, present state is S2. Input is 0, then where it is going? It is going to S0 and equivalent binary is 0, 0. So next state is 0, 0. Present state is S2, 1, 0. And if input is 1, then next state is S3. So S3 means 1, 1. So see, state diagram is very important. Once you will be able to draw state diagram, you can design this circuit very easily. If present state S3 and input is 0, if input is 0, it will go to state S2 and S2 is 1, 0. If present state is 1, 1 and if my input is 1, then next state is S1. That is 0, 1. And only here output is 1. At every other place output is 0. So only here output is 1 and at remaining places output is 0. Okay, so now I know present state, I know next state, I know expected output, I know the external input. See, this is sequential logic circuit. It means we can design this sequential logic circuit using flip-flops. So now I know what is present output of flip-flop. I know expected next output of flip-flop. But I don't know what input I should apply to flip-flops. So I'll design this sequence detector using JK flip-flop. JK flip-flops. So from present output and next expected output, when we want to identify values of inputs, we use excitation table. So here, by using excitation table, I'll find values for JB, KB, because I have two outputs, so I'll use two flip-flops. Input to flip-flop B is JB, KB, and here it is JA, KA. Okay, so let's write excitation table for JK flip-flop. For 0, 0, J is 0 and K is don't care. For 0, 1, 1 don't care. For 1, 0, it is don't care 1. The detailed description how to get excitation table is already explained in working of JK flip-flop. The link is given in the description box. There I have explained why we are getting don't care 1 here. 1, 1, it is don't care 0, or you can remember it as 0, 1, don't care, and here it is exactly opposite, don't care, 1 and 0. So this is excitation table for JK flip-flop. Now to find values of JB, KB, we need to compare this QB with QB plus here, and then we'll get JB, KB. So see here, 0, 0. QB is 0 and QB plus 1 is also 0. So for 0, 0, J 0, K don't care. 0, don't care. Again 0, 0. So again 0, don't care. Next is 0, 1. See here what I am doing. I am simply comparing this present output with next output. QB with QB plus 1. So 0, 1. It is 1 don't care. 0, 0. 0 don't care. 1, 0, don't care 1, 1, 1, don't care 0, 1, 1, don't care 0, 1, 0, don't care 1. Similarly, for JAKA, I'll compare this QA with QA plus 1. So for 0, 0, 0 don't care. For 0, 1, 1 don't care. See, I am writing from this excitation table. So it is very important to understand excitation table or to remember excitation table. 1, 0, don't care 1. 1, 1, don't care 0. 0, 0, 0 don't care. 0, 1, 1 don't care. 1, 0, don't care 1. And for 1, 1, don't care 0. So now by using excitation table, our truth table is ready. Next step is, so see, our state diagram is ready, state table is ready. By using excitation table, we have created our truth table. Next is by using K-maps, we'll find simplified equations. 4 K-maps for 4 inputs, JA, KA, JB, KB. And what we have at input side, we have QB, QA and X. So MSB here, QB, QA and X. And here we use gray code. So 0, 0, 0, 1, 1, 1, 1, 0. Because in gray code only one bit changes at a time. 0, 1. See here. Values are 0, 0, 0, it means 0, 0, 0, 1 is 1, 0, 1, 1 is 3, 0, 1, 0 is 2. Then 1, 0, 0 is 4, 1, 0, 1 is 5, 1, 1, 1 is 7, 1, 1, 0 is 6. I have prepared separate video related to how to prepare K-map. In that you will get the details. But see here, it is always like 0, 1, 2, 3, 4, 5, 6 and then 7. Now let's put values of JA. So here you'll see JA is 0, 1, don't care, 0, 1, don't care, don't care. Then 0, 1, don't care, don't care. Again 0, 1, don't care, don't care. So let's make a group. What I can do is I can make group of adjacent or overlapping ones. And here for don't care, I can consider them 1 or 0 as per requirement. So I'll consider these two ones as don't cares as 1. So I'll make this chord. And for this chord, equation is JA is equals to, here in QB, both values are different. And here in this, QA is 0 and 1, so we can't take QA. Whenever value is same, we can only take that variable. Here X is 1, here also X is 1. So JA is equals to X. For KA, let's put values for KA. KA is don't care, 1, 0, don't care, 1, 0. Don't care, 1, 0. Don't care, 1, 0. So here what I can do is I can make overlapping ones, group of overlapping ones. If I'll fold my K-map from here, then I can make group of these two ones with these two don't cares. So I'll have to compare between these two columns. So here KA is, here QA is 0, 1. So I can take QA, X is 0, 0. So whenever value is 0, it means we take bar of that variable. So JA is X, KA is X bar. Similarly, let's put values for JB, KB. For JB, what we can do is we can make this pair because we have only 1, 1. And here nothing is common. Here we need to take both variables because we can't compare it with any other column. So QA is 1. So I'll write QA as it is. X is 0. So I'll take X bar. Next, here what we can do is we'll make these two pairs. This is my first pair and this is my second pair. So equation will become, for this pair, equation is QA bar X bar plus, here both are 1, 1. So QA X. So this is like A bar B bar plus AB. Equation of X NOR gate. QA X NOR with X. Now we know equations for inputs. Now we need to identify equation for output as well. So I'll have to make one more K-map. So here for output Y, all are 0. Only 1, 1, 1 is 1. So only 1, 1, 1 is 1 and all others are 0. So here what I can do is, there is no don't care, no other one. So I can make pair or chord or anything. So what I can do is I'll make group of only 1, 1. And then for output Y, equation is, here QB is 1. So QB. Here QA is 1. X is also 1. QA and X. So this is equation for Y. Now based on these equations, let's draw the diagram. Number of flip-flops are 2. So I'll draw 2 JK flip-flops. These two are my flip-flops. Here you can see QB is my MSB, QA is LSB, and that is why I have drawn B to left hand side and A to right hand side, because this will generate my most significant bit. Now this is synchronous circuit. So I'll connect single external clock to both the flip-flops. Positive edge triggered or negative edge triggered. So here I'll write negative edge triggered. This is single external clock connected to both flip-flops. JA is X. So I'll connect X here directly. KA is X bar. So I'll connect an inverter here and through that inverter KA. Next is JB. JB is QA into X bar. It means we need to take one AND gate. And what are inputs to AND gate? One input is QA and another input is X bar. Then KB. my KB is QA X NOR X. So I'll have to take X NOR gate. X NOR for KB, and inputs are, one input is QA, another input is X. So these are inputs for my flip-flop B, these are inputs for my flip-flop A, and my final output Y I'll get by using AND gate. There is multiplication of these three variables, so I'll use AND gate, which has three inputs. Here I'll get output Y, and inputs are QA, QB and X. QA, this is my X, and QB. So here I'll get output Y. So in this way I can design sequence detector. Once you'll implement this sequence detector on breadboard or using any board, and when you'll connect these gates, and when your input sequence will come as 1011, then your output will become 1. So thank you so much for watching this video. I hope you understood how to design sequence detector using Mealy Machine. In next video, we'll see how to implement same sequence detector using Moore machine. Thank you for watching. And don't forget to like to this video, subscribe to my channel and share this video with your friends. Thank you.